we'll go through problem by problem and come up with a strategy, and you'll tell me whether every step makes sense, so that you know that you can eventually do this by yourself. Is that okay? Right? So there are 5 problems, all of equal weightage. Problem 1, 2, 3, 4, 5. When I'm a student, I always try to look at the sheet, spend a minute trying to pick out the or arrange them in an order where I go after the easiest ones first. So in that sense, in your mind, you should have an idea of which are the easy ones, which is the one you will do first. Okay. So if you are about halfway through the exam and you have secured, let's say 70, 80 points, that will make you feel better than trying to do everything in the second half. Okay. So when I look at this, and if I try to compute the or see which ones I'll go first, to me P1 looks like the obvious choice to try first because it doesn't involve any mystery. You read problem 1, it says using the data for velocity and pressure below, compute the total rate of change of pressure for x equal x and time equals 3 seconds. Like it asks for x equals 0, 10, and 20. So it's just a calculation for so P1. Identify what needs to be done. Need to calculate the total rate. Is there an extra copy? Please give it. Rate of change of pressure at x comma t. So we are doing mock exam, just discussing the solutions to this mock. Discussing this mock exam. So need to calculate the total rate of change of pressure at x comma t. So that starts with trying to understand what is it mathematically, and that is equal to the rate of change of pressure locally or at a given x value plus velocity times dp over dx, and v is nothing but dx over dp. So what do you need? You need partial p over partial t, partial p over partial x, and v at a chosen x and t values. So we'll be specific. Let's say we pick x equal to 0, t equals 3.0 seconds. I'll do that for one value of x. The remaining two you can do it yourself later. So v is dx over dt, or this has to be delta x over delta t. Sorry, v is already given. My bad. V is already given. At x equal to 0, t equals 3 seconds. V is 2.10 meter per second. This is already given. So I don't need it here. So V is given. I want to calculate what is partial P over partial T. That is, I'll say this is the pressure at 3 seconds. minus the pressure at 2 seconds divided by 3 seconds minus 2 seconds. And all this is at x equal to 0. So you have to look up the pressure at x equal to 0 and time. There is column 1. We are solving this complex. Sorry?
Yes, 2 seconds. Why did you choose 2 seconds?
Because in my table, the data is presented as 0, 1, 2, 3. If I want the derivative at 3, I have to look one step back. Thanks for the question. So this would be 171 minus 141 kilopascal divided by 1 second, or this is 30 kilopascals per second. If your data was presented in steps of 0.5, you would do 3 minus 2.5. Yes. For time derivatives, it would make sense if I say the speed or rate now may depend on the past, but it cannot depend on the future. So I have to do backward differencing and not central differencing or forward difference. For spatial domain, it's okay, but even there are some, especially in supersonic and hypersonic flows, the information that you are moving can only come from downstream and not from upstream. So even there, you can't do forward differencing in some cases. But good question for our purpose. Time derivative always look backward difference. So we got the first term. This is 30 kilopascal per second. We got that. So now we need to get, I'm going to speed up a little here, the pressure gradient partial P over partial X, that will be delta P over delta X. Here you can do forward differencing or central differencing, but at time 0, okay, so this I'm going to write is the pressure at x equals 10 meters, 3 seconds, minus the pressure at 0 meters, 3 seconds, divided by 10 meters minus 0 meters. So this will get me 151 minus 171 kilopascals divided by 10 meters. So I get minus 20 kilopascals per meter. This is pressure gradient, meaning it's like the gradient always means space or spatial derivative. It's right?
Wouldn't it be 2?
Yeah, sorry. So that will be 2. 20 divided by 10. Yeah.
So would it be incorrect if we did 20, like pressure at 20 meters minus pressure at 0 meters, since 10 is in the middle? Because it's not that kind of.
X equals 0. So I guess let me clarify here. So you have the table of data for 0 meters, 10 meters, 20 meters. and then time points 0 seconds, 1 second, 2 seconds, 3 seconds. We are interested in this combination. Okay, so if I want the time derivative, it makes sense for me to look one step backward. If I'm interested here, okay, and I want the spatial derivative, I don't have anything behind me. I don't have minus 10. I can only look forward. And I have to use that. Yeah. Yes, you could. You could. You can do it three ways. You can do central, backward, forward. As long as you are aware of what you're doing. You can say, I am using a central derivative approximation for 10 meters and proceed. You can do that. Central is exactly central derivative or forward. Central or forward is not okay for time derivative because the present cannot be influenced by the future. It has to be influenced only by past. Okay. So I'll say backward difference, no forward or central. But for spatial derivative, this is forward. So this is forward, but backward or central can be used with justification. Great questions. Thank you. So I have here the term velocity is 2.10 meter per second multiplied by -2 kilopascals per meter. So that gets me minus 4.10 kilopascals per second. So the total derivative would be 30 minus 4.10 or 25.90 kilopascal per second. Does this make sense? Are we okay? Are we all together? Yeah.
Is the question not just asking that part that
Question is asking you to get this quantity. The question is asking you for compute the total rate of change of pressure at x equals to 0, 10, 20 and time equals 3 seconds. So the total rate is the sum of the local plus the spatial or convective. Okay. Come again.
goodness, you just you added 2.15 to instead of multiply.
2.1 times 2 is 4.20. Maybe I'm better at fluid mechanics than arithmetic. Sorry, 25.80. That is why I give like only 5 to 10% weightage for the final answer, because I know if I took the exam, I'll mess up something. Are we good? Can we move on? Second problem. Everybody's okay? Yep, each value you need to repeat for x equals 10 and x equals 20. So for 10, you could do forward, backward, or central difference. For 20, you have no other option but to do only backward or central. You can't do forward because there is no other value after 20. Here. Something not clear? Something not clear?
Yeah, just now.
Can we move on? Yes, okay. In my ordering, actually, I should have looked at problem 3. Problem 3 is also quite easy. To take a look, it is from chapter 5. It asks you to calculate average velocities. It gives you a velocity profile and asks you to calculate the average velocity for different values of n. Okay, so we'll try this. Can I erase this? Do you just want to take a picture?
Yeah. It's recording.
Somebody uses the recorder. So problem 3, the velocity, an appropriate turbulent pipe flow velocity profile is V vector equal to UC times 1 minus R over R raised to the power 1 over N I cap. So that is like writing. So we'll call this direction X or I cap. What they are saying is the velocity is purely axial and that velocity looks something like this. And this curve is given by UC 1 minus R over R to the power 1 over N. We are asked for need to compute the average velocity. What is average velocity? How will you think of it? So if you take a control volume, let's say you draw an arbitrary control volume. At this surface, we'll call it 1. The flow comes in with a velocity profile. At surface 2, if we assume some uniform velocity, some constant velocity, we'll call it, let's say U average. Okay. U average times the cross section area is equal to the flow rate of V dot N dA. This is the definition for average velocity. Definition for average velocity. It is the uniform velocity magnitude that leads to an identical volume flow rate. So U average equal to 1 over pi r squared, which is the area, integral What is v dot n? V dot I cap. So if this is the area, we have this being n, and n is nothing but minus I cap. That's the outward drawn normal. Outward drawn normal. Okay. So we have this. Sorry, we have this times d. So that is like, right, actually I should write this is 0. That will get me u average equal to 1 over pi r squared. What is this? UC 1 minus r over r to the raised 1 by n times 2 pi r dr. R equal to 0. We talked in length about why this is 2 pi r dr. Refer to the notes. So I don't want to repeat it again. So I have UC times 2 divided by r squared. And then I have 0 to r, 1 minus r over r dr. One over. It's a very straightforward integration. What I would do is make the substitution r over r equal to, say, theta, which means dr is r d theta. So wherever r appears, I have to replace it with r times theta. So I'm going to get u average equal to 2uc divided by r squared. And if I have to convert this from r to theta, 0 will map as 0, r will map as 1. R will map as 1. So I have 0 to 1, theta equals 0 to 1, 1 minus theta to the power 1 over n, r theta, r d theta. So I do have a r squared here, so I can get rid of that. So I have 2uc, 0 to 1, theta, 1 minus theta to the n, d theta. How many of you remember enough from your previous calculus courses to do this integral? If I left it to you to do this, what will be your strategy? What shall we do about this? This is like a expression. If you expand, it will become an infinite series. We don't want to do that. So what do we do? Substitute 1 minus 0 or 1 minus theta. Substitute 1 minus. I'll rewrite it here. So substitute 1 minus theta equal to some new variable, we'll call it t, so that d theta becomes minus dt. Okay, and theta becomes 1 minus t. And the limits, you want to go from theta to t, 0 to 1 will map as 1 to 0. So this integral is going to become 2 times UC 1 to 0 1 minus t times t raised to the power 1 over n minus dt, which becomes 2 UC 0 to 1 t raised to the power 1 over n minus t raised to the power 1 over n plus 1 dt. Now it's not a terrible problem, still doable, right? So I'll do U average equals 2 times UC times t raised to the power 1 over n plus 1 minus t raised to the power 1 over n plus 2 divided by 1 over n plus 2. And I have to apply this from 0 to 1. Obviously, the lower limit goes to 0. Only the upper limit is going to stay. So 2 UC n divided by n plus 1 minus n divided by n plus 2, which is going to get the 2 UCn plus 1 n plus 1 times n plus 2. I'll rewrite this separately. U average is U center line multiplied by 2n divided by n plus 1 times n plus 2. You may ask me the question, what's the point of doing this math problem and getting an algebraic expression in the end? In this module, we are just trying to learn how to use this integration or how to use this definition of average velocity. This average velocity and this centerline velocity and this velocity profile, they all have physical meaning, which we'll see when we do chapter 8, which is pipe flow. Okay. For now, learn the mechanics, learn the technique, and put a box around this expression. This is the answer we want to present. So if this is an exam problem, getting this answer is basically 90% of the credit for you. After that, plugging in n value, those are like minor steps. Yeah. So the limits are 1 to 0. When I flip the limits, that negative will be taken. For problem 2, I'm going to give you really 3 minutes. I'm going to keep quiet and then we'll pick it up. Problem 2, please take a look. Seems like we're struggling to read something. Have you taken a read at problem 2? Yes. The fluid is going through a nozzle or a converging duct between A to F. It enters with a velocity V naught. It exits with a velocity that is 50 times higher, 1.5 times V naught. The duct is contoured in a way that the flow accelerates along the streamline or along the direction of the flow. What we are asked to comment is sketch the component of acceleration. But even without doing that, look at the figure B, where they have plotted the velocity as a function of position along the duct. Let's play 20 questions. Okay. Look at figure B, and I'm asking you, what is the velocity between A and B like? Which means the velocity is not changing. So if the velocity is not changing, what is the gradient in velocity? 0. So it means between A and B, the velocity gradient is 0. Even though the velocity itself is not 0, what is the acceleration between A and B? 0. Right? So let's try to understand each segment. Okay, so I'm first interested in between A to B. What is the velocity? Velocity is V naught, and the change in velocity, none, the constant, which means velocity gradient is 0, which means V partial V over partial X is V naught times 0 equal to 0, or the spatial component of acceleration is 0. For those to whom it looks obvious, good for you. For those for whom it didn't look obvious, here is the reasoning. Please make a note. Okay. So are we good with between A and B? Everybody is agreeing to this. Good. What is happening between B and C? Is the velocity, how is it trending? How is the velocity trending? We are playing 20 questions. Answer my question. Down. So between B and C, the velocity is trending down. It goes from a value to a lower value. Okay, which means what can you comment about the gradient? If you go along the flow, velocity is decreasing, which means this quantity partial V over partial X, it's like delta V over delta X. Since delta V is decreasing, this is negative. Right? So as a consequence, acceleration is negative, or it's decelerating, in other words. Am I making it too obvious now? Like, is it easy to follow, or is it too boring? I mean, like making it too easy. Good. Okay. Between C and D, what's happening to the velocity? Between C and D, the velocity goes from a low point, it reaches a peak. This is C, this is D. Velocity is trending upwards, right? So trending upwards, which means acceleration is positive. It's continuing to accelerate. So it was not accelerating between A and B. it was decelerating. It reached a value that is even lower than V naught. So over here, you are at V naught. At C, the velocity was, so this is B, V naught. At C, the velocity is lower than V naught. Okay. And at D, the velocity is reached the maximum. So acceleration is zero, I'm sorry, greater than zero between C and D. Can you now reason for between D and E? Between D and E, is the fluid accelerating or decelerating? Decelerating. Okay. Here is my next question. Is the acceleration between D and E a constant or changing? Okay, I'm going to draw this out. So remember, this acceleration is V partial V over partial X. Okay. If the slope is constant, or if V is constant, which means the slope is zero, that means acceleration is also zero. Look up, please. No need to write. Look up. I'll give you time and let you write. If velocity is constant, acceleration is zero. This is like between A and B. If velocity is changing, okay, and the slope is negative, that means acceleration is negative. Or if the slope is positive, acceleration is positive. This is the case between B and C. This is the case between C and D. Okay. Now think about the slope. The slope, if the slope is constant, what does that mean? If the slope is a number, fixed number that is non-zero, what does that mean? It means acceleration is a constant. It's constantly increasing or constantly decreasing. Velocity is changing, but at a constant rate. If the slope itself is, the slope is decreasing, what does that mean for the acceleration? It is accelerating, but at a ever decreasing rate, right? Which means acceleration itself is decreasing. The best way to understand deceleration or acceleration, to me at least, is to look at the national debt. The national debt is just through the roof. We all know that. If this year, let's say $5 trillion were borrowed, and let's say next year $3 trillion were borrowed, how will you say that in words? Which means the debt is still growing, but the growth rate has come down. It means if acceleration is decreasing, that's like saying the velocity is still increasing, but at a lower rate. Okay, so look at the situation between D and E. Between D and E, here is how the graph looks like. Here is D at a peak, and the graph reaches E like here. What can you tell about the slope of this curve? The slope of this curve, it's non-linear. It is initially zero. So at D, the slope is zero. Slope is zero. But over here, the slope is negative. But compare at this point, it's negative. Compare it to this point. Is the slope less negative or more negative here than here? So I'll call this D1. I'll call this E1.
Yes.
So between D1 and E1, the slope is decreasing. And at E, the slope is zero. So between D and E, the velocity is still increasing, or so the velocity is decreasing, the acceleration is also decreasing. Okay, so what you should be able to do is to look at p of x and be able to infer the slope and the curvature, or the rate at which the slope itself is changing. Okay, and what goes on between E and F? E and F also means acceleration is zero, constant velocity. Okay, so I'm obviously looking for you to be very familiar with this spatial derivative and understand A based on V and the gradient in V. Okay. In this problem, we didn't see a situation where V itself was negative, but the gradient is positive. But those things could happen when we see turbulent flow or flow behind objects and recirculation and stuff like that. But at least here it's kind of straightforward. Is it making sense? How to look at the velocity profile and be able to think about acceleration. Yes. So in such a problem, I would have a table. I would ask you to fill out the table and do your work separately. So like in this problem, if this exact problem were appearing, I would have a table that looks like this. A to B, acceleration, kind of give you like choices, 0 or increasing or decreasing. And then you fill out for A to B, B to C. If there's only one thing I'm asking, I'll put it in words and expect you to provide that. But if this is like trying to fill out a table, you just have to fill out the table, and you still have to include the details of your work. I still need to see that, but the table has to be there. If there is a table, don't leave it blank. That's my message. Okay, I still haven't done the momentum balance problem, which is problem 4. Let's do that.
Is that all for? Streamline?
There is yes, as a mock problem, I just copied it from the book. But if I were asking it in the exam, I wouldn't ask you to sketch it. I would ask you to comment on it, because sketching is far more complicated. So please look at problem 4 and we'll talk about how to solve. So it looks like a thermodynamics problem. Air at T1, P1 and V1 enters the venturi as shown. The air leaves at T2, P2 and V2 is of course not given. Calculate the horizontal force required to hold the venturi stationary. atmosphere pressure is given as 101 kilopascal. You are asked for the horizontal force required to hold the venturi stationary, but you are also kind of not provided the V2. So how will you calculate V2 in the first place? Exit velocity. Louder, please. No, momentum balance will only get you the force. Or to do the missing velocity, you still have to think about mass balance. See, we learned only two concepts. Number one, mass balance will help you calculate one missing quantity. That one missing quantity could be like an inlet or exit velocity, and momentum balance will typically, or not typically, will require inlet and outlet velocity and help you get a force or pressure. This is the game plan for all the problems related to control volume analysis. It will typically involve you to apply a mass balance and compute a missing quantity and then use that in the second step to compute a force. In our case, we'll draw our nozzle. Okay. I'll draw only half of that. And I'll say my control volume coincides with the shape of the nozzle. Okay. So there is, if I were to do the mass balance, I have m dot in and I have m dot out. Since we have a steady flow, this can obviously mean only m dot in must be equal to m dot out. That's why I said it's like a thermodynamics problem. So that is like writing density inlet at the inlet times velocity at the inlet multiplied by area of inlet equal to density at the outlet, velocity at the outlet times area at the outlet. So we are given only a single value for inlet and outlet velocity. If it's not explicitly stated, we'll assume this is the average value. That is why we are able to write the equation this way instead of writing an integral. So if I want the inlet density, that will be the pressure inlet divided by R for air times the inlet temperature. P equals to R. B in, A in equal to pressure at the outlet divided by R for air times the temperature at outlet, VO A. I like this kind of a convenience where if I can write it this way, I don't have to worry about the gas constant. And I need to solve for V naught. I'll write that is equal to V in multiplied by the pressure ratio multiplied by temperature ratio multiplied by area ratio. So that is 303 over 101. Outlet temperature is 220 Kelvin over 300 Kelvin. Multiplied by area ratio, which is 0.6 divided by 1. Inlet velocity itself was given as 0.5. So you can compute what is V naught in meter per second. Can someone tell me? 0.66. Okay. Thank you. So V naught is 0.66. Yeah.
The problem kind of similar to this last class.
Yeah.
We found we needed one of the initial velocities. Or, I think it was the exit velocity.
That is the exit velocity.
But when we did it this time, we used the mass balance and we split the integrals with the control surfaces.
That's because we are not given a velocity profile. We are just given a single velocity. In that problem, did we do integration?
Yes.
Here we are not doing integration precisely because we weren't told the velocity varies as a profile or anything. We were just told V1 is 2.5. And since that's what I wrote here, since that only a single value is provided, we'll take that as the average across the cross section. Okay, so now listen up, please. That at least we are able to get the exit velocity 0.66 meter per second. Why do we need a force to hold this thing in place? What is the need? The fluid is coming in at 2.5. It's bringing in a lot of momentum or some amount of momentum. It is leaving it at only 0.66, which means it's not leaving with all the momentum it came in. Some of the momentum is used to exert a force on the structure, and that's why you need to hold the structure in place with an external force. Okay, so if you recognize that there is a force missing here, then you need to compute that. Okay, and to do that, look at the control volume. Okay, look at the control volume. What are the forces on this control volume? Can you tell me? What are the forces acting on this control volume? Pressure force. So I'll have to draw pressure as always compressive, P1. And on the other side also the pressure will be compressive, P2. Okay. So those are the two forces. And then I have to figure out what is the force that I need to apply to hold this in place. I'll call it F, which needs to be determined. Okay. So can I erase this side? Can I erase this side? So my force balance is like saying integral rho v dot n dA for the control surfaces equal to sum of all the external forces. This is the equation for momentum balance. Of course, we are not going to do the integration because we are going to write this is minus rho V1 V1A1 plus rho V2 V2A2 equal to P1A1 minus P2A2 plus the unknown force. This is the momentum inflow. This is the momentum outflow.
Since rho is a constant, since density is a constant,
Rho is not a constant. Rho is dependent on the existing temperature at section 1 and section 2. So you'll have to write rho 1 and rho 2. My bad that I missed that, but rho 1 and rho 2 are different. And this is the pressure force at 1. This is the pressure force at 2. And this is the unknown force we are trying to solve for. So the unknown force would be rho 2 V2 squared A2 minus rho 1 V1 squared A1 minus P1 A1 plus P2 A2. We are given pressure 1, pressure 2. We can get this through ideal gas equation. We can also get this through ideal gas equation. We know V1, we got V2 from mass balance. This is given, this is given. So everything is given. You have to compute for, you have to compute force. What I'm hoping you would do, even if you don't have to do all the annotations like I do, but if you write an expression like this and that expression is correct, you have already secured 90%, then plugging in the last 10%. Yes.
It's the sign for the momentum side or the signs for that reverse.
I just wrote them in. I wrote the positive term first and the negative term second.
Okay.
I didn't reverse any sign. It's still
Okay,
negative.
you did on this. Okay. I just, how it was written out, I thought you moved the.
No, I didn't want to put a negative term as the first term, so I wrote this first, followed by this, and then I brought these two to the other side. Their sign changed. Always differ plugging in numbers until you are like settled that this is the expression. Don't plug in at these steps, get here and then substitute. Can we discuss the last problem? Problem 5. The supposed challenging one. Maybe not so challenging. To make it a little interesting, I want you to take problem 5. Calculate the temperature reading variation with time, not the rate. I just want you to write calculate the temperature of a probe attached to the okay, calculate how the temperature of a probe attached to the external body of a helicopter will vary with time. Essentially, strike down the words the rate of, the rate at which. Strike these words. Now let's answer that problem. Calculate how the temperature of a probe attached to the external body of a helicopter will vary with time. The helicopter is ascending vertically through a cold region where the surface temperature is -5 degrees Celsius and the temperature drops at a rate of 1 degree Celsius per 250 meters. The helicopter climbs at a rate of 10 meters per second to reach 1.5 kilometers height to maintain the same altitude. That is, describe the story from 0 to 1.5 kilometers, and that's it. You don't have to worry after that. Take a minute, read it, get back to you. Can I erase this? Everyone? Yes. So the helicopter is let's say here is where the helicopter initially is. We'll call this z equals 0, and it starts climbing up. Okay, so we'll mark this as z positive. So it starts climbing up at a rate of 10 meters per second. So dz over dt is 10 meter per second, or you can call this the velocity in the z direction is 10 meter per second. The temperature drops in the vertical direction. The temperature drops in the vertical direction at a rate of 1 degree Celsius per 250 meters. And since it's a drop, I have to include a negative sign. As you go higher, it drops, so it has to be negative 1 degree Celsius per 250 meters. Okay. The helicopter starts at the ground and climbs up to 1.5 or 1,500 meters. $1,500. Now, what are you asked to compute? You are asked to compute how will temperature change with time. If it uniformly climbs at 10 meters per second, how many seconds will it take to reach 1,500 meters altitude? 150 seconds. So we are interested in time 0 to 150 seconds. You have to plot how temperature will change with time in this time window. You need T of T, temperature as a function of time. Okay, so what's the next step? The air is steady, stationary. The temperature of the air is changing only with height, but at a given point, the temperature is not changing with time. That is, if you take any particular height, the temperature here, T of Z, would be Ts minus the rate of change of temperature or temperature gradient multiplied by delta Z or multiplied by Z, since this is Z equal to 0. Yes.
Couldn't you just make 6 plots between,
6 what? 6 plots?
6 plots between 0 and 1500 on the D side, and then draw a curve, and then subtract 1 degree for every plot?
Okay. You want to start at minus 5 degrees Celsius, and for every 30 seconds, you want to do what? What do you want to do?
Let me think about it. I might have been wrong.
It would have to be intervals of 25 seconds,
Intervals of 25 seconds.
because every 25 seconds you go up 250 meters.
So when you say it drops by 250 meters, that's like saying, that's like the measurement interval. But if you, what happens if you travel 125 meters? It would be half a degree drop. Or what happens if you travel 375 meters? It would be 1.5 degree drop. It's not like it doesn't magically change from 0 to 250. It doesn't magically drop by 1. It's a continuous drop.
Isn't that the point of the curve?
Yeah. Because if you
Right, this,
if you drew a point at
Mm.
T equals 25,
Okay.
it'd be go up to negative 6 degrees Celsius.
so you want to draw a straight line between minus, oh sorry, the other way.
Right.
So you want to draw this, let's say 25, 50, 75, 100, 125, 150 time in seconds. So you start at minus 5 degrees Celsius. You want to go from here to here, and this would be minus 6 degrees Celsius.
Yes.
And you are saying we should just continue this straight line until we reach 150 seconds, where we would have attained minus 11 degrees Celsius. That's one of the responses. We can check whether that is correct. Okay. The only thing I see as a problem here is your estimation doesn't factor in the fact that the helicopter itself is moving at a certain rate. You're not. Oh, you're saying that is this 25 seconds.
Yeah, 25 seconds.
Okay, maybe it's another way to get to the same answer. So what I was going to show you is the use of the total derivative. So we have dt over dt equals the derivative with respect to time at a given z value plus dz over dt times the temperature gradient, which is nothing but Vz, which is nothing but 10 meter per second. So this term is 0 because temperature is steady and not changing with time. So this would be 10 meter per second multiplied by minus 1 degree Celsius divided by 250 meters. So that gets me minus 1 degree divided by 25 per degree Celsius per second. Yeah. So if I want temperature as a function of time, I would integrate between 0 to t, dt of t, which gets me minus T divided by 25 degrees Celsius. That is time in seconds, which amounts to the same thing that you said. Good. This will be good. Can you tell me exactly how you got this? Because did you factor in did you consider that this is uniform? Or what if this were not uniform? How would you update your P? Suppose the helicopter is not ascending uniformly. Suppose it is accelerating. Let's say the acceleration is something like 10 times T. It's if itself it becomes a function of time. Actually, wait. Let me just make sure people write this down, then we'll discuss the second piece. That's quick thinking. I like it. I want you to reason how you will do it when the ascent is nonlinear.
Velocity will not be linear on the actual exam.
I'm not denying that statement. We have 10 minutes. Let's see what all changes we can make to this problem.
If you did it 10 times T, could you not make two graphs where it's the height in seconds and then you have meters and seconds on the other graph? So in your first graph, you'll have the time on the right side. So say if it was 10T and T equals 1, we go where
See, instead of doing such a two graph system, if you are ultimately interested in the time domain, that is why you have this quantity. I mean, the whole you are by reasoning with two graphs, you are bypassing this quantity. What I'm saying is everybody good with this so far? We are going to discuss modifications. Okay.
Well, what I was thinking in like regards to this thing, you could just integrate the velocity by itself and turn it into a placement.
Equation for Z.
Yeah, since we know that the helicopter starts at 0, so we just need to integrate it whenever that C is 0.
You can do it in many ways. So if ultimately you want this quantity, which happens to be velocity a constant. If the acceleration, that is, let's say the helicopter's velocity, so modification 1, let's say the helicopter's velocity Vz is given as V naught times 1 minus exponent of minus time over 150 seconds. Something like this, which means at long time, the velocity goes to 0. No, sorry. We'll put it this way. E power minus T over 150, something like this. Because this means initially it's accelerating. As it reaches its cruising altitude, it slows down and eventually this function will go to 0. Yeah. With me? So this function will look like this. Okay. So you are initially climbing quickly, which means you are traversing this initial height quickly, which means what? The temperature initially will drop faster. Later, the drop will slow down. So if I go back here, this is what is dz over dt? That is Vz as a function of time multiplied by the same minus 1 degree Celsius divided by 250 meters. Vz is V naught exponent of minus T over 150. So if I want the temperature as a function of time, I'll have to integrate this. That is going to be V naught multiplied by the temperature gradient exponent of minus T over 150 divided by minus over 150. This is my temperature as a function of time. How will this function look like? Instead of being linear, it will it will drop. It will drop quickly and then flatten. The initial drop is quick. You reach your height sooner and then you flatline there. If your height is not changing, your temperature is not changing. Okay. You can accelerate in many ways. If you talk to people who operate helicopters, they may tell you we always have a low acceleration at the beginning, then the acceleration picks up, then we kind of reach a plateau and then we come down something. So this waveform or this velocity, it could look something like this. Or it could look something like this. If you are able to understand the velocity itself can change with time, and the velocity factors in here, if velocity is a function of time, this rate becomes a function of time. If velocity is constant, the rate is constant. If rate is constant, what does it mean? The temperature changes linearly. If the rate is either an increasing function or a decreasing function, temperature changes non-linear. So this is again, maybe for the exam, I'll tell you, be prepared to tackle problems in which the velocity is a function of both space and time. Temperature or pressure is a function of both space and time. So this idea plus the fact that acceleration is local plus spatial, the total derivative dp over dt is local plus spatial. You are getting two problems with these ideas involving acceleration, involving total derivative. Okay, I'm telling you that two problems are appearing. I made the exam, I know. Okay. We have about 5 minutes. Is there anything you want to ask me? Yes.
But this type of problem, are you adding the second dimension?
No second dimension. We are doing, I want you to focus on a one-dimensional problem, but being able to use this equation for either velocity or for pressure or temperature. Yeah. No, yeah, that's maybe something you learn, but not for this exam. Maybe we'll tackle that in the comprehensive, like the final exam. Yeah. But if it is along a streamline, it reduces to 1D. We will that is totally game. So this x can denote not just a linear x, it could also denote length along a streamline. So this is, yeah, one dimension in that sense also. It need not be linear in dimension. It could be along a line. Good question. So two problems on this. One problem on mass balance, which is like an average velocity calculation. One problem on momentum balance, which is like a force calculation. Okay, and then one problem that combines elements of this with the control volume analysis. Okay. So today's participation exercise, please work out the solution to all the 5 problems by Tuesday or even next week, I don't care. Upload the solution to the mock exam for 1 point credit. I won't grade it. I'll just look at, if you have a submission, you get a point. That's it. Okay. Thank you.
You said bring these back